Hello everyone. In this video, I'm going to show you that sometimes when you apply L'Hopital's rule to evaluate indeterminate forms, it might lead you to strange situations. So it might lead you to nowhere and you won't be able to evaluate the limit. And in such situations, I'm going to share with you a technique that you may try to use in order to evaluate the limit. So let's look at these two limit problems here. First problem. So if you're looking for limit of this expression as x approaches infinity, so we know that this limit has the form infinity over infinity. So as x goes to infinity, numerator goes to infinity, denominator also goes to infinity. So if you apply L'Hopital's rule for this limit, then we'll get here limit as x approaches infinity of the derivative of the numerator, so that is equal to 1 over the derivative of the denominator, which is equal to 1/2 times the quantity 1 plus x squared raised to negative 1/2 times the derivative of the base, which is equal to 2x. And this expression can be simplified to limit as x approaches infinity of, you have square root of 1 plus x squared, and then all over x. So this limit is again in the form infinity over infinity. And if you apply L'Hopital's rule again, we'll get here limit as x approaches infinity of 1/2 times the quantity 1 plus x squared raised to negative 1/2 times 2x, the derivative of 1 plus x squared. And then all over the derivative of x, which is equal to 1. And our expression is again equal to what? Its limit as x approaches infinity of x over square root of 1 plus x squared. So as we can see from this limit problem, so applying L'Hopital's rule is not helpful. So therefore, how do we evaluate this limit? So in this case, we can try actually algebraic method to evaluate the limit. If you still recall how to compute the limits at infinity of a rational function, our strategy is to divide the numerator and the denominator by the highest power of x in the denominator. And actually, we can use the same technique in evaluating this kind of expression, wherein you have a radical expression. But in this case, if you're thinking of the highest power of x in the denominator, you have to consider the radical as well. So in this case, our highest power of x in the denominator, it's like square root of x squared. So that is just x raised to 1. Therefore, to determine the limit, we may first divide the numerator and denominator by x. So we'll get here x divided by x over square root of 1 plus x squared, and then over x. And we may put this x here inside of this radical symbol, and we'll get here limit as x approaches infinity of 1 over square root of 1 over x squared, and then plus x squared over x squared. So keep in mind that x can be written as square root of x squared if x is greater than 0. And as x goes to infinity, our x is positive. So simplifying our radicand, we'll get here limit as x approaches infinity of 1 over square root of 1 over x squared, and then plus 1. And clearly, the limit is equal to, so this goes to 0 as x goes to infinity. So our limit is just equal to 1 over square root of 1, which is equal to 1. Now, let's look at the other limit problem. So this limit problem has again the form infinity over infinity. And if you want to clearly show that it is indeed infinity over infinity, this one, it's clear that it goes to infinity. But how about this one? But of course, this one has a higher base, so we would expect that the numerator will go to infinity as well. But if you want to show that the numerator is indeed going to infinity as x approaches infinity, then you may write this numerator here. So this is like limit as x approaches infinity, factor out 5 raised to x, and you'll be able to write it as 1 minus 3 raised to x over 5 raised to x, which is 3 over 5 quantity raised to x, all over 2 raised to x, and then plus 4 raised to x. Since the base here is between 0 and 1, then we know that this exponential function will approach 0 as x approaches infinity. So therefore, this will be like infinity times 1, so it will go to infinity. So this has an indeterminate form, infinity over infinity. And if we apply immediately L'Hopital's rule to compute for the limit, what do we get? So this is applying L'Hopital's rule, we'll get here limit as x approaches infinity of what is the derivative of 5 raised to x. So the derivative is 5 raised to x ln 5, and then derivative of 3 raised to x is 3 raised to x ln 3, and then all over 2 raised to x ln 2, and then plus 4 raised to x ln 4. And clearly, L'Hopital's rule here is leading us to nowhere. Why? Because again, this is an indeterminate form, infinity over infinity. And if you apply L'Hopital's rule again, what you get is what? This is the same thing, but this is quantity squared, and then quantity squared, quantity squared, and then quantity squared. So therefore, how do we evaluate this limit? So here we may use again a similar strategy as in evaluating limits of rational functions at infinity. And what is that strategy? It's like dividing the numerator and denominator by the dominant term in our denominator. It's like the highest power of x in the denominator. So if we look at this denominator here, what is the dominant term here? The dominant term is 4 raised to x. So what we can do here is to first divide the numerator and denominator by the dominant term in the denominator, which is 4 raised to x. So we'll get 5 raised to x over 4 raised to x minus 3 raised to x over 4 raised to x all over 2 raised to x over 4 raised to x, and then plus 4 raised to x over 4 raised to x. And this is just equal to limit as x approaches infinity of 5 over 4 raised to x minus 3/4 raised to x, and then all over 2 over 4, so that is 1/2 raised to x, and then plus 1. And what is the number approached by the function values as x approaches infinity? So since the base of this exponential function is greater than 1, we know that it will go to infinity as x approaches infinity. Here, the base is less than 1, it will go to 0. And then again, base is less than 1 here, it will go to 0. Therefore, our numerator will approach infinity and our denominator will approach 1. So what's the limit? It's equal to infinity. So when you apply L'Hopital's rule and it leads you to strange situations, you may try to compute the limit by algebraic methods. Sometimes you have to do some algebraic manipulation and then apply L'Hopital's rule in order to determine the limit. Okay, so that's all for this video. Thanks for watching and hope to see you next time.